everyone, we are Group 6 and today we will be presenting our problem-based learning project for subject DAU 14403 Algebra. The title of our project is Arithmetic and Geometric Sequences, Terminal Expansion of a Piston Rod. This project focuses on applying mathematical concepts, specifically arithmetic and geometric sequences, to a real-life engineering problem involving terminal expansion. Our instructor for this subject is Madam Nohalisa. This slide shows the members of Group 6 who were involved in completing this project. The group's members are Khadijah Maisara, Aiziana, Nurul Ain Nasiha, Nur Fatih Nazira, and me, Nur Afika. Each member contributes equally in terms of discussion, calculation, analysis, and preparation of the presentation slide. Through teamwork and collaboration, we were able to complete this project successfully. For this slide, I will explain the problem statement of our project. The piston rod in an internal combustion engine is exposed to rapid heating and cooling during engine operation. As a result of this continuous temperature change, the piston rod experiences thermal expansion, causing its length to increase gradually over time. When this process happens rapidly over many operating cycles, the expansion may accumulate and cause the piston rod leg to exceed the maximum safe limit. Exceeding the safety limit can lead to serious mechanical issues such as engine malfunction, reduced efficiency, and in extreme case, engine failure. This situation also poses potential safety risks to users and may increase maintenance and repair costs. Therefore, it is important to develop a method to model and predict the change in piston rod length over time. In this project, arithmetic and geometric sequences are used to represent the pattern of thermal expansion to determine the operating cycle at which the piston rod becomes unsafe.
In this presentation, I will explain our FILA table, which stands for fact, idea, learning issue, and action plan. This table helps us understand and solve the problem of piston rod expansion using arithmetic and geometric sequence. First, for the fact, the piston rod expands and contracts due to heating and cooling in each operation cycle. The initial length of the piston rod is 100.0 mm. This expansion happens continuously over many cycles. The piston rod can expand in two ways. It can expand by a constant amount of 0.8 mm per cycle or by a constant ratio of 1.008 per cycle. The number of cycles involved in represented by n. Second, the idea we model the expansion of the piston rod using arithmetic and geometric sequence. The arithmetic sequence is used to represent linear expansion where the length increases by the same amount each cycle. The geometric sequence is used to represent proportional expansion where the increase becomes larger over time. Using this sequence, we calculate the length of the piston rod at a specific cycle, Tn, and the total expansion up to cycle n, Sn. Moving on to the learning issue. First, we need to understand what arithmetic and geometric sequence are and how to calculate the nth term Tn. Next, we need to learn how to calculate the sum of the first n term, Sn, for both sequence. We also need to understand how these sequences are applied to real-life engineering problems. Lastly, we need to determine the cycle number when the piston rod reaches an unsafe length. For the action plan, we refer to Diploma Level Mathematics textbook to understand the formula and concept. We also use online learning resources such as YouTube and other educational platforms to strengthen our understanding of sequence and series. In conclusion, the filler table helps us organize information clearly and apply arithmetic and geometric sequence to analysis piston rod expansion in a real engineering context.
So, for the parameter that provided for group 6 include an initial piston rod A1 of 10310 mm, a constant increase per cycle in the arithmetic model D of 0.5 mm, a crude ratio R of 1.005, and for the geometric model a maximum safe piston rod length M of 0.5 millimeters. All the calculation and graphical analysis in this study are based on these values. So, the analysis begins with the arithmetic sequence model, in which the piston rod is assumed to expand a constant amount during each operating cycle. The piston rod at the end cycle is given by Tn equal to n1 plus n minus 1 multiplied by d, while the total expansion over multiple cycles is calculated by Sn equal to n divided by 2 multiplied by 2a1 plus n minus 1 multiplied by d. So, these models represent a linear expansion resulting from uniform heating. After the calculation has done, using the arithmetic model, the piston rod at cycle 15 is calculated to be 110.0 mm. The piston rod reaches and exceeds the maximum safe limit at cycle 16, making it the first unsafe cycle. So, the corresponding graph displays a straight line trend, indicating steady and consistent growth throughout the operating cycles. This confirms assumption of a constant heat effect in each cycle. So, let's continue with the geometric sequence model. Is then considered where the piston expansion of the piston rod increases proportionally with each cycle. This model reflects the effect of accumulated heat and increasing material fatigue. The piston rod length at the end cycle is given by Tn equal to A1 multiplied by R to the power of the n minus 1, and the total expansion is calculated by Sn equal to A1 multiplied by R to the power of the n minus divided by the quantity R minus 1. Unlike the arithmetic model, this approach represents accelerated rather than constant expansion. So, using the geometric model, the piston rod length at cycle 15 is approximately 110.42 millimeters, which exceeds the maximum safe length. As a result, the piston rods become unsafe at cycle 15 yearly than predicted by the arithmetic model. So, as you can see, the graph shows an upward curving trend, indicating an increasing rate of expansion over time and confirming that the geometric model predicts faster growth. For this slide, we are comparing the values of an arithmetic sequence and a geometric sequence. For the arithmetic sequence, the values produced are 103, 103.5, 104, and so on until 112.5. Each term increased by a constant difference of 0.5, which means the growth is linear and uniform. When the values are plotted on the graph, they form a straight line and the gradient of the graph remains constant. In contrast, for the geometric sequence, the values start at 103 and increase to the 103.52, 104.03, and so on. Each term is multiplied by a constant ratio rather than increased by a fixed amount. As a result, the increase between terms is not constant and becomes larger as the values increase. When plotted the graph forms a gently increasing upward curve. So, in conclusion, the arithmetic sequence shows steady, consistent growth, while the geometric sequence shows growth that accelerates over time. That's all for the calculation parts. So next, for this part, we compare the sum of the values for the arithmetic sequence and the geometric sequence. For the arithmetic sequence, the sum increases as a 103, 206.5, 310.5, 415.0 and continues up to 2155 and 0.0. Although the sum increases steadily, the increase in the sum is not constant. When we plot the sum against the term number, the graph forms a smooth upward curve. This happens due to the cumulative effect of linearly increasing term. On the other hand, for the geometric sequence, the sum values are 103, 206.52, 310.55, 415.10, and 216.85. The initial sum is similar to that of the arithmetic sequence, but as the number term increasing, the sum grows more rapidly. As a result, the curve of the geometric sum becomes steeper compared to the arithmetic sum. In conclusion, both sums increasing over time, but geometric sequence show a faster growth in the total sum as the number of terms increases. So, we move on to the final part of solution. In this slide, we present the overall comparison between the arithmetic and geometric sequence. In terms of individual values, the arithmetic sequence grows at a constant rate, which results in a linear graph. In contrast, the geometric sequence grows at an increasing rate, showing gradual exponential growth. In terms of the sum of values, the arithmetic sequence shows a moderate cumulative increase. However, the geometric sequence shows a faster cumulative growth due to the multiplication by a constant ratio. As a result, the sum curve of the geometric sequence rises more steeply than that of the arithmetic sequence. Overall, arithmetic sequences are suitable for the steady growth, while the geometric sequence represent growth that accelerates over time.
For this discussion, we focus on two main parts: model behavior analysis and factor affecting the result. First, for the model behavior analysis, the arithmetic model shows a steady and uniform increase in the piston rod length. This means the head effect is assumed to be constant in each cycle. On the other hand, the geometric model shows a faster rate of expansion. This indicates the head effect accumulates as over time. When the temperature is higher, material fatigue can occur, causing the piston rod to expand more rapidly. Next, for the factors affecting the result, temperature variation during engine operation plays an important role. Besides that, material properties such as the coefficient of thermal expansion and fatigue resistance also affect the expansion. Uneven cooling between cycles can increase the expansion rate. Lastly, engine load and the during of operation also influence the results. Overall, these factors explain why the expansion behavior differs between the arithmetic and geometric models.
Good morning. For this slide, I'll be talking about the whole conclusion. In conclusion, the expansion of the piston rod was successfully modeled using arithmetic and geometric sequence. The arithmetic sequence model represents constant expansion, which is suitable when temperature change causes a fixed increase in length. The geometric sequence model shows increasing expansion over time, reflecting the effect of accumulated heat. This model proved that piston rod expansion can be analyzed and predicted mathematically. Overall, the study shows that mathematics play an important role in engineering by helping to understand physical change and support safer mechanical design. Thank you. That's all from our Group 6.